All right, let's just jump right into it. Have you ever actually stopped to think about how scientists manage to measure the weight of an atom? I mean, it's a completely mind boggling problem when you really sit down and think about it. You can't exactly take a single microscopic atom, pluck it out of thin air with invisible tweezers, and just drop it onto your kitchen scale, right? They are unimaginably small. So, how on earth do we know their mass with such incredible precision? Well, it turns out the answer involves a brilliantly clever scientific workaround, and as you'll see, a massive twist that completely redefined how we look at the building blocks of our universe.
Welcome to today's Explainer. We are going to dive right in and crack the code of weighing the invisible together. It's essentially a microscopic scientific detective story, and we get to explore a fascinating complication researchers stumbled upon along the way. A little complication that proves nature absolutely rarely likes to keep things simple.
So here is our roadmap for today. First, weighing the invisible. Number 2, the carbon-12 standard. 3, the isotope twist. 4, inside the isotope. And finally, number 5, the real-world elements. Okay, let's kick things off with section 1, weighing the invisible. Since a single atom obviously can't be weighed on a traditional balance, we desperately need a specialized way to compare them. And the solution to our invisible weight problem comes in the form of this incredibly sophisticated instrument called a mass spectrometer. It's basically a giant atomic racetrack. Notice the process happening here. Atoms or molecules are first ionized, which just means they're zapped and given an electrical charge. Then they're accelerated at super high speeds. Finally, as they fly through the instrument, they separate according to their mass. But here's the thing. Because we're doing this to a batch of different atoms, we aren't getting traditional weights in pounds or grams, we're getting relative values. We're literally just seeing how heavy one atom is compared to another.
Which perfectly sets up section 2, the carbon-12 standard.
Now, here is the catch. If you're only finding relative mass, just comparing things to each other, you desperately need a universal anchor point. Like if I tell you a boulder is 10 times heavier than a rock, that doesn't actually help you unless we both know exactly how heavy that specific rock is, right? Scientists needed a rock, and the element that was officially crowned the universal standard, carbon. Specifically, the exact isotope known as carbon-12. One single atom of carbon-12 is given a mass of exactly 12 units. And from this, we get our atomic mass unit, which is precisely 1/12 the mass of that carbon atom. But why carbon? Well, carbon is practically everywhere. There are far more chemical compounds containing carbon than literally any other element in the universe. So it makes perfect sense to use the most chemically social element, essentially the prom king of the periodic table, as our ultimate baseline. And looking at this data brilliantly illustrates how that relative comparison plays out across the whole periodic table. Let's use a fruit analogy, because that makes it super easy to picture. If we pretend hydrogen, the lightest atom with a relative mass of 1, is a single little grape, then carbon, our standard anchored at exactly 12, would be like a nice little bundle of 12 grapes. Make sense? Now look down at calcium at 40. A single calcium atom is exactly 40 times as heavy as a hydrogen atom. So calcium is like a heavy grapefruit compared to our hydrogen grape. And gold, all the way down there at 197, is essentially a massive watermelon. Every single relative atomic mass on this list is beautifully, mathematically anchored by that carbon-12 standard. All right, moving right along to section 3, the isotope twist. So with carbon-12 as our gold standard, the problem was totally solved, right? We just weigh everything against carbon, write it down, and call it a day. Well, not quite. Enter the twist. For a really long time, the expected rule of thumb was that pure samples of an element were absolutely 100% uniform. It was just assumed that every single atom in a pure sample of carbon, or hydrogen, or chlorine was an identical clone with the exact same mass. But when researchers actually started analyzing the masses of various elements, the actual discovery was a total shock. Pure samples are actually a mishmash of different weights all living together. Even in a completely pure element, the atoms themselves had varying masses. This discovery absolutely disrupted the whole idea of identical atomic clones.
So how on earth can an element be pure yet have atoms of different weights? The resolution to our mystery lies in a concept called isotopes. An isotope is defined as atoms of the same element that have the same number of protons and electrons, but a different number of neutrons. So the absolute crucial takeaway here is the rule of 3. Same protons, same electrons, different neutrons. You see, the protons and electrons dictate what the element actually is and how it behaves chemically. But the neutrons, they're basically just freeloaders. They're just sitting there in the nucleus adding extra dead weight without changing the chemical identity.
Let's look a little closer at this in section 4, inside the isotope. Let's actually peek under the hood of our gold standard, carbon, and see exactly how these invisible variations happen in nature. Look right at the numbers here. There isn't just one type of carbon. There's carbon-12, carbon-13, and carbon-14. Notice how the protons and electrons stay entirely locked at 6 all the way down the list? That number 6 is carbon's unbreakable identity card. But look at the neutrons column. Carbon-12 has 6 neutrons. Carbon-13 has 7. Carbon-14 has 8. That changing number of neutrons in the nucleus is entirely responsible for the changing mass number of the atom. It's the exact same chemical element, just carrying a slightly heavier backpack.
And what is truly wild to me is that this doesn't just happen with heavy, complex elements. No way. It happens with the absolute simplest building blocks of the universe, too. Even the lightest element, hydrogen, has variations. Standard hydrogen has 1 proton and literally 0 neutrons. But nature also gives us deuterium, which adds 1 neutron, and tritium, which has 2 neutrons. Every single one of them is hydrogen, driven entirely by the addition of those silent, heavy neutrons.
Which brings us to our final part, Section 5, the real-world elements.
So, okay, we know these subatomic variations exist, but how do these different versions of atoms actually mix together in the world around us? Well, if you were to gather a natural sample of neon gas, you wouldn't just be scooping up one type of atom. As you can see, the vast majority, about 90.5% of your sample, would be neon-20, which has 10 protons and 10 neutrons. But hiding right there inside that exact same pure gas is a nearly 10% chunk of neon-22, which is a heavier isotope carrying 12 neutrons. There's even a tiny, tiny fraction of neon-21 just floating around in there too.
Now, let's look at chlorine. This one is really fascinating. If you take a sample of naturally occurring chlorine, 75% of it is chlorine-35, containing 18 neutrons. But look at that. A massive 25% slice of your sample, literally 1 out of every 4 atoms, is the heavier chlorine-37 isotope, packing 20 neutrons. It's a huge variance right inside what we'd otherwise call a pure element.
And all of this brings us completely full circle to how we actually define an element's weight in the real world. Because practically every element is a naturally occurring mixture of these different isotopes, scientists can't just pick one and ignore the rest. They have to average them out. And that gives us the true, updated definition of relative atomic mass. It is the calculated average mass of all the naturally occurring atoms of an element, carefully weighted by how abundant each isotope is, all measured on a scale where our super reliable carbon-12 atom is exactly 12 units. It's honestly truly amazing when you step back and think about it. What started as just a quest to weigh the invisible led to the discovery that the building blocks of our reality are far more diverse and complex than we ever imagined. The elements we breathe, drink, and interact with every single day aren't just uniform clones. They are rich, statistical mixtures of isotopes, varying only by a few silent neutrons. So I'll leave you with this to ponder. If simply adding a single uncharged neutron can entirely change the weight of an atom, how do these tiny, invisible differences shape the physical properties and the chemistry of the vast world around us?